Hello everyone, this is Michael Abdelmalak. I'm going to present to you a poster for a student contest entitled as Deep Learning Approach for Power System Stability Assessment. First, I would like to go through what we did in details. We are trying to train a convolutional neural network in order to assess the rotor angular stability based on the utilization of heat map images that represent the power system stability behavior. So why we need to do that? Because the process to assess the dynamic performance has become more important to maintain the reliability of the grid, especially against extreme weather events. The second is that although time-domain simulation approach provide very accurate results, it is a computationally time-involved process. And on the other hand, direct methods, which usually consume less time, it lacks the observability of system states in some cases. So our proposed strategy is implemented in two phases. First, we need a numerous amount of system failure cases to be simulated, and the results are saved as heat maps. Then these heat maps or images are used to train the convolutional neural network. The approach is applied by following the flowchart. First, the numerous amount of failure scenarios are simulated using Monte Carlo simulation. At each iteration, we generate a random value representing the location, the clearing time, and also the loading factor. After solving the time domain simulation using Euler approximation, we obtain a profile for the voltage, magnitude, and angles, which are converted into an image that represents the heat map. Then these heat maps will be used to train the convolutional neural network. So a single phase at bus 7 is represented for illustration of the approach. Here, as you see, when a fault occurs at bus 7, the voltage profile has not changed in stable or in an unstable behavior. However, the angles have completely different profiles. The heat map in the unstable scenario shows very high regions of pink and purple color. So if we merge the three graphs of representing magnitude, angles, and angle deviations, we are able to generate a red, green, blue image, an RGB image, which is the fourth image below all the graphs. This is what we call it the heat map representing the system. So in a stable region, mixture values occur, but in an unstable region, the dominant colors are usually pink or purple color. By identifying these colors, we could use these images to train the convolutional neural network and be able to forecast the system stability in advance. Now, this work is still under progress. For now, we just using the convolutional neural network to monitor and assess the system stability via time domain simulations. We also introducing the heat map approach to represent the power system stability profile. In the future, various convolutional neural network configurations can be applied to enhance the performance and the accuracy levels of these neural networks. It is expected that this approach will provide a faster way to assess the stability compared to time domain simulation, and it also will provide an easier way to determine the most impacted generator units during instability behavior.